The machine built to reveal the hidden structure of matter has instead deepened uncertainty. After finding the Higgs boson in 2012, the Large Hadron Collider has found no other expected particles for over a decade. And now, a faint anomaly that is not yet a discovery but is strong enough to reopen questions many thought were fading has appeared in the data. The real question this video answers is why the latest anomaly at CERN is reopening the reality debate. And by the end, you will understand exactly what the evidence eliminates from the old model, what the result still has no account for, and why the mechanism or interpretation stays open. The core spark is this: when data does not fit the categories physics prepared, the result is not a clean breakthrough, but a widening fight over whether the missing answer is a new particle, a new framework, or evidence that the search has been aimed at the wrong question. What is known is that detectors reached unprecedented sensitivity. What is unclear is whether the patterns now appearing are signals or noise. What else could create the same effect is detector artifacts, statistical flukes, or miscalibrated backgrounds. What would confirm or falsify the explanation is reaching the 5 sigma threshold, which requires a 1 in 3.5 million chance of being a fluke. Here is one small payoff before we go further. Physicists created a new official label called structured background with undetermined origin for patterns that are not random noise but are not clear particles, which means classification itself has become part of the story. You can reality check this by looking at recent CERN publications, where this label now appears in official summaries. The default story is straightforward. The Large Hadron Collider was built to smash protons together at the highest energies ever achieved in a laboratory. The standard model of particle physics predicted the Higgs boson, and finding it would confirm the mechanism that gives particles mass. Once the Higgs was found, the next step was supposed to be finding the next layer: supersymmetric particles, dark matter candidates, or at least some clue pointing beyond the current theory. The old model assumed that pushing to higher energy and higher precision would reveal new particles, the way turning up the power on a microscope reveals new structures. Contradictions get dismissed because physicists have a concept called the look elsewhere effect. When you search in thousands of places for a signal, you practically guarantee finding meaningless patterns that look like breakthroughs. Any anomaly below the 5 sigma threshold can be explained as statistical noise, and dismissing it protects the field from false discoveries. The memory of the 750 giga-electron-volt mirage in 2015, when a massive data spike vanished in later runs, reinforced this caution. The result is that even when detectors register something unexpected, the institutional reflex is to wait for more data rather than announce a discovery. Here is the first anchor contradiction. Collision data now shows an unexpected cluster of 4 lepton events that deviates from the standard model in a historically clean channel. The old model predicted that 4 lepton events should follow a smooth distribution with no excess in any particular energy range. What actually exists is a small but persistent bump in the data that appears across multiple detector subsystems and multiple years of operation. The mismatch is this: if the standard model were complete, the bump should not exist. And if it were random noise, it should not persist across independent datasets. This changes the equation because 4 lepton channels are among the cleanest in particle physics, meaning there are fewer background processes that can fake a signal. The persistence across years means the pattern is not a one-time fluke. The next loop tightens the contradiction. High-precision measurements found the W boson is significantly heavier than theory predicts, a direct contradiction of fundamental physics. The Standard Model gives an exact prediction for the W boson mass based on its relationship to other particles. The measurement from the collider detector at Fermilab found the W boson mass to be 7 standard deviations heavier than the Standard Model allows. If the theory were correct, the measurement should match within error bars. What actually happened is the measurement broke through those bars, with a confidence level that makes random error extremely unlikely. The micro-reframe is that this is not a small discrepancy you can adjust with better calibration. It is a direct challenge to the internal consistency of the Standard Model. The reinforcement line is this: when a particle that has been measured thousands of times suddenly weighs more than the entire framework allows, the framework itself is under pressure. Another contradiction deepens the pattern. Beauty quarks are decaying into electrons and muons at different rates, defying the law of lepton universality. The Standard Model treats electrons and muons as identical except for mass, so they should appear in decay products at the same rate when mass differences are accounted for. Multiple experiments at the Large Hadron Collider and at the Large Hadron Collider Beauty experiment have measured a consistent deviation where muons appear less often than electrons in certain beauty quark decays. The old model predicts equality. The measurement shows inequality. The significance has grown with each new data release, now sitting in the 3 sigma to 4 sigma range, depending on the channel. The micro-reframe is that lepton universality is not a minor detail. It is a foundational symmetry of the Standard Model. The reinforcement line is that if one symmetry breaks, it opens the door to other symmetries being approximate rather than exact, which would require a completely new layer of physics to explain why the approximation holds as well as it does. Here is where the silence becomes louder. After finding the Higgs and nothing else for over a decade, physicists feared a scenario they called the nightmare. Finding the Higgs and no other particles, leaving no clues for what lies beyond current theory. That is exactly what happened. The Large Hadron Collider has now run at higher energies and recorded more collisions than any machine in history. The detectors reached unprecedented sensitivity, meaning they can see smaller signals and rarer processes than ever before. The old model assumed that higher energy would reveal supersymmetric particles, or dark matter candidates, or some exotic structure that would explain why the Higgs mass is so much lighter than mathematical models suggest. What actually happened is precision null results. 0 clean signals for the specific new physics everyone expected to find. The micro-reframe is that the silence is itself a form of data. The reinforcement line is that when you build the most powerful microscope in history and see nothing where you expected to see everything, the question shifts from what is there to why is nothing there? The classification problem sharpens the tension. Detectors occasionally register particle paths that appear to come from nowhere or vanish, and physicists now use the label structured background with undetermined origin to describe patterns that are too organized to be noise, but too unstable to be particles. The old model assumes that every real signal will eventually reach the 5 sigma threshold, if you collect enough data. What actually happens is that some patterns hover in the 3 sigma zone for years, neither disappearing nor strengthening. The current anomalies are stuck in this lower zone, which means they are statistically interesting, but not yet discoveries. The micro-reframe is that the label itself is an admission. The categories physics prepared do not fit the data. The reinforcement line is that when the detector sees something and the framework has no box to put it in, the framework is incomplete. Another layer adds pressure. Data sifting algorithms discard 99% of collision data in real time, leading to fears that the discovery of the century is being deleted automatically. The Large Hadron Collider produces a petabyte of data daily, which is far more than any storage system can handle. Algorithms called triggers decide in microseconds which collisions to keep and which to discard. The triggers are programmed to look for known signatures: high-energy jets, missing energy, lepton pairs. If a new particle produces a signature, the triggers were not designed to recognize. It will be deleted before any human ever sees it. The old model assumes the triggers are comprehensive enough to catch anything important. What actually exists is a filtering system that is optimized for the particles we already know. The micro-reframe is that discovery depends not just on what the detector can see, but on what the algorithm decides to save. The reinforcement line is that a revolutionary finding could be sitting in discarded data right now, and there would be no way to know. The institutional dimension becomes visible. Billions of dollars are tied to specific theories, making it politically and financially difficult for CERN to admit a potential dead end. The Large Hadron Collider was sold to governments and funding agencies on the promise that it would find supersymmetry, dark matter, or at least some clear path beyond the standard model. When the Higgs was found and nothing else appeared, the narrative shifted to higher luminosity and longer runs. The current plan is to upgrade the collider and keep running until 2040. The old model assumes that patience and more data will eventually produce a discovery. What actually exists is a situation where the longer the silence lasts, the harder it becomes to justify the next round of funding. The micro-reframe is that the search is now constrained not just by physics, but by the need to maintain institutional credibility. The reinforcement line is that when the machine built to answer the next question has run for a decade without answering it, the pressure to reinterpret marginal signals grows. One more loop closes the circle. Multiple detectors have reported a small recurring hint of a new light particle near 95 giga-electron volts, but it refuses to reach the discovery threshold. The signal appears in different channels: photon pairs, tau pairs, bottom quark pairs. The old model predicts that if a real particle exists at that mass, the signal should strengthen as more data accumulates. What actually happens is the signal fluctuates, sometimes growing, sometimes fading, but never crossing 5 sigma. The look elsewhere effect explains some of this. If you search across enough energy ranges, you will find random clusters. But the fact that the same energy keeps appearing in independent channels is harder to dismiss. The micro-reframe is that the signal is either the edge of a real discovery or the most persistent statistical ghost in the history of particle physics. The reinforcement line is that after a decade of silence, even a ghost starts to look like evidence. So why is the latest anomaly at CERN reopening the reality debate? The evidence eliminates the assumption that higher energy and higher precision alone will reveal the next layer of particles. The result still has no account for why the W boson is heavier than the standard model allows, why beauty quarks violate lepton universality, why 4 lepton events cluster where they should not, and why a faint signal near 95 giga-electron-volts refuses to disappear or strengthen. The mechanism or interpretation stays open because the data is strong enough to rule out pure noise, but not strong enough to confirm a specific particle. What this changes for your understanding is that the crisis at CERN is not just about missing particles. It is about whether the framework itself is aimed at the right question. The standard model fails to explain 95% of the universe, including dark matter and dark energy. The measured mass of the Higgs suggests our universe is in a metastable state and could technically collapse at any moment. Critics argue that if the Large Hadron Collider finds nothing else, physics may shift from experimental science to untestable mathematical philosophy, a transition some call post-empirical physics. The anomalies now appearing are not clean discoveries, but they are also not dismissible noise. They are evidence that the categories prepared by theory do not match the patterns appearing in data. The next clue to watch is whether the signals strengthen as new data arrives, or whether they fade into the same silence that has defined the last decade. If you want to see how the evidence evolves, subscribe and turn on notifications so you do not miss the next update.